Hello, good morning everyone. Welcome to the 70th IFC Day 2. We are just about to start the video presentation session. The first video is by Mr. Michael Farnshuster. He is from Inductotherm US, his manager sales. His topic is Industrial Internet of Things and Big Data Processing in Industrial Environments. Mr. Huster is a graduate from Rowan University in Accounting and Finance, has worked his way up in several departments of Inductotherm. He works with foundries and companies that use induction melting and heating equipment in their manufacturing processes. At present, District Manager of Indiana and Kentucky and Mid-Atlantic East Coast. He plays an active role in American Foundry Society, Northern Indiana chapter as the chairman. Internet of Things is the latest technology-driven adaptation for Industrial 4.0 revolution. As we progress towards technology transformation and deployment, this is one of the key focus areas where foundries need to adapt and work towards. So Inductotherm has stepped up and come up with this great topic. Let's hear it from Mr. Huster.
Hello, my name is Michael Farnshuster with Inductotherm Corp, and I am going to present on digitization challenges to data collection and meaningful use in today's IoT-driven world. The last year has made a big impact on everyone's lives. Many aspects of our lives have been heavily changed, including travel, society, work, and how we spend our time. The last year has also brought forth lots of changes to businesses and industry. We see the same changes and many more, including remote work, video conferencing, travel and shipping, digital technology, adoption, market demand shifts, and labor shortages. These labor shortages are driving more changes, which will continue in the future, most notably driving automation, augmented reality, the IoT, artificial intelligence, and machine learning. These technologies come together to train someone and make them as productive as fast as possible, to make someone as efficient as possible in their position, or to fill in for or substitute this missing labor. All these technologies are trends that we will continue to see forward, especially the Internet of Things and machine learning or artificial intelligence. So what is the Internet of Things and machine learning? The Internet of Things is part of the fourth industrial revolution. This graphic shows Industry 4.0 or the fourth industrial revolution and the previous industrial revolutions before it. The first industrial revolution began in the early 1700s in Great Britain and was categorized by the steam engine, water power, and mechanization to replace manual labor. The second industrial revolution began later in the 1800s in the United States and is categorized by the assembly line and mass production using electricity, for example, Ford's Model T car assembly line. The third industrial revolution began in the later 1900s and is categorized by computers and automation. The fourth industrial revolution, or Industry 4.0, was coined in Germany in the 21st century and is categorized by the Internet of Things and cyber physical systems. This is a current and ongoing revolution which is still changing and evolving. As a basic overview of the Internet of Things, it all starts with the devices or things, which include sensors, actuators, and other devices and data they collect. The next step is the Internet connection and data transport and access, making this information available to us. This is done through a variety of PLCs, routers, gateways, and much more. The next part is storing and organizing the data for analytics. This is done on a local or cloud server and is organized for easy access from dashboards, machine learning algorithms, and APIs. Then you get to your final and most important step, the value gained from either the human interaction with dashboards or the results and actions generated from machine learning. The data stored from IoT devices is often called big data. And depending on the application, it can consist of huge data sets. As mentioned, this data is stored and organized on cloud or local servers using a variety of tools. This data is then used for artificial intelligence and machine learning, which is a form of advanced analytics that learns about data and looks for patterns, trends, and insights. Machine learning is used to drive all sorts of things, currently including fraud detection, chatbots, and recommendation engines, which including serves as ads on websites and shopping rankings. But it is also hugely beneficial to the industry. To give you an idea of the importance of the Internet of Things and big data, here's a quote from Bill Gates. If you invent a breakthrough in artificial intelligence so machines can learn, that is worth 10 Microsofts. If the fourth richest man in the world who started Microsoft raves about the importance of artificial intelligence and machine learning, you know it must be good to pay attention to it in the future. So how do you deploy such an important technology? We will go over the development of IoT applications and AI and the challenges encountered. This is a general topology or visual representation of an IoT application. Similar to the IoT diagram we went over earlier, you have the sensor layer, the communication layer, and the data and server layers, and the resulting API dashboards and machine learning results. There are different challenges encountered at different steps of implementing IoT in industry. They include the fear or risk of cybersecurity problems, the lack of standardization in sensors, communication protocols, and more. Legacy or old equipment installations, upfront investment costs, initial unskilled worker base that would need training, data integrity when worrying about human error or noise, internal system barriers specific to different applications, and the current technology liability, fear of new technology and being outdated quickly, and social, political concerns. We will focus more on the technical challenges rather than the general business or political concerns. Here's one of the lackings of standardization. This pie chart shows the most common industrial protocols used. The largest protocol, Allen Bradley's Ethernet IP, is only used 15% of the time. There are many different types of protocols out there to support it. This is just one example of the lack of standardizations during digitization and data collection. Some more challenges of data collection is making sure data collected meets the following criteria. All these need to be considered when collecting data. Garbage data gives garbage results. They are completeness of data, whether it's missing any parts, the consistency of the data across different systems, if it accurately represents real-world values, its integrity to be used in machine learning, and timeliness. Got to make sure it's available when needed. I'm going to briefly go over a few aspects of data integrity in data collection for machine learning applications. One aspect is small or unbalanced data sizes. This can be including too much good data and not enough bad data or failures for use in machine learning. For example, in the casting industry, too many good parts and not enough defects. This can actually make training an algorithm very difficult. Another is semi-supervised data. This is a cross between supervised data or labeled or classified data that you will use to feed or train an algorithm, and unsupervised raw data. Semi-supervised data is when you try to use a mix of data to train an algorithm. Then heterogeneous data, data that is formatted or scaled differently, or different units is not easily compared to other data. And finally, siloed data. Data collected or stored and held in a group of organization that is not easily accessible to the rest of the organization. How data integrity applies to training of the machine learning algorithms can be difficult to understand. So here's an example I've heard made before. Think of machine learning algorithm as a black box. If you feed it data, it will give you results. You're trying to feed it data to be able to tell a dog apart from a wolf. You start by feeding it sets of data classified as dogs and many different photos of dogs, and then the same for wolves. After the training is done, you get the results after testing, and it gives you the correct result. It classified this background as a dog. However, inside the black box or algorithm, it came to a conclusion. Photos of a dog or wolf with a person must mean it's a dog. And a lone photo of the dog or wolf will classify it as a wolf. This is just an example of how an algorithm may give the correct result with small data, but may have been trained incorrectly. Photos of dogs maybe more often have people, but in just this one aspect to be factored into a final resulting algorithm. And the last challenge we'll go over is data security, which is also an important aspect of data collection. It is a good practice to keep data encrypted during transportation and storage, as well as keep IoT devices secure. There are instances of industries being targeted like the Colonial Pipeline hack, which occurred earlier this year. Now, during Inductotherm's development of our MyPlant IoT product, we had to take in consideration of all the challenges we just went over. At Inductotherm, we build foundry equipment for melting metal, furnaces, power supplies, and other supporting equipment. So similar to the previous topologies, we use an IoT gateway device to collect data over multiple different protocols on the local network from different equipment and IoT devices, and then digitize the data securely and transport it to the cloud using Azure's IoT Hub encryption to be securely stored in the cloud for use in machine learning and dashboard and human access. This provides the meaningful use of IoT and AI. We'll now go over some of the uses and impact Industry 4.0 has on businesses, as well as some examples of what we're working on at Inductotherm. As mentioned before, the Industrial Internet of Things is not a destination. It's a tool to provide value, and it must provide value and have meaningful uses. Here are some of the benefits or advantages of Industry 4.0. Improving operational efficiency and productivity as the highest priority advantages. Proving and opening up new business opportunities. Reducing downtime, utilizing assets more efficiently, and being able to sell products on a service instead of a one-time cost. Reduce the cost of assets, enhance safety for workers, and being able to innovate current process rapidly and being able to understand the customers better. This is a real-world existing example to show the impact of IoT and machine learning. This features a technology company that happens to make steel, which is Big River Steel, company from Arkansas, USA. Big River Steel uses IoT and machine learning for many uses, including demand prediction. Big River accurately predicts demand for steel using machine learning models using macroeconomic data, historical demand for steel, manufacturing activity, and the activity of large consumers of steel. Sourcing and big inventory management. Big River predicts the availability of scrap and hedges for future events. Scheduling optimization. The optimization models maximize energy consumption at off-peak times and thus minimize energy costs. As well as production optimization. Big River uses machine learning models and can predict when events like breakouts and cobbles are most likely to happen and minimize their occurrence. Predictive maintenance. Big River uses machine learning models to identify the optimal times to maintain key equipment. The transportation optimization. Big River works with customers and shippers to minimize the costs of outbound transportations. At Inductotherm, we're focusing on the same uses of machine learning that pertain to the melting and heating portion of the foundry operation. This includes data access analytics, helping managers to visualize and efficiently make sense of what is going on in real time. Process optimization. Melting processes can be optimized to increase efficiency and reduce costs. Predictive maintenance. Equipment problems can be predicted using analytics before they occur. And training. Foundry workers can be brought up to speed faster. This is an example of Inductotherm's MyPlant IoT dashboard, which shows data collection from equipment and IoT devices. It shows a mix of equipment metrics, charts, and analytics to help managers efficiently track the performance and maintenance of their equipment. And as mentioned, we're going to focus on the process optimization and predictive maintenance and displaying alerts from these analytics. We are focusing on the areas to be able to provide value and cost savings. Areas like saving on energy costs. This gives the process recommendations like close our hood during this period. Items like reducing downtime, predictive maintenance through water drain, inlet analytics, and more. Labor training and time utilization. Train your labor force faster and give them the tools to utilize time efficiently. Increase production rate. Optimize power utilization by broadcasting time lost due to limitations in the plant. And increase product quality and consistency. Recording all melt data and sensor information for quality management. There may be challenges to implementing IoT and machine learning in foundries, but the benefits outweigh the challenges. We must be flexible and adapt to our new technologies to keep our competitive edge. Thank you, everybody. I appreciate your time.
This was a great eye-opener presentation by Inductotherm US, and we virtually thank Mr. Huster for his time and effort in making this presentation. A lot of takeaways from this that the big data part on the foundries is the most essential thing.
Hello,
now.
everyone. I'm Kukhyun Han.
So the big data and real-time data collection and machine learning is going to be the way forward, and Inductotherm has taken a great step forward in coming up and helping the foundry community in general. Thank you, Inductotherm. So next speaker, the next video is by Mr. Hyun Han. He's the president of Samyang Machinery, Korea. The topic today is a study of applicability of sand 3D printing cores and molds for casting application. Can you start the video, please?
A president of Hello, everyone. I'm Han, a president of Samyang Machinery in Korea. So first of all, thank you very much for inviting me to the 70th Indian Foundry Congress. So I'd like to say congratulations on your anniversary. So the title of my presentation today is a study on the applicability of sand 3D printing cores and molds for casting applications. So this is contents of my presentation.
Being the Foundry community in general. Thank you.
I'd like to introduce our company, Samyang Machinery, first. So Samyang is the only company that leads the design and manufacture of core parts for medium-speed engines by combining 46 years of technical know-how and 3D printing technology. We do producing locomotive, marine, and inland power plant medium-speed engine core parts, such as pistons, cylinder heads, cylinder liners. And also we do sand 3D printing services. And recently we launched our own industrial 3D printers. Okay, let's move on to the main topic. So first, why 3D printing? This graph shows the additive manufacturing market size globally. So as you can see, the additive manufacturing market size in 2020 is about 13 billion US dollars. So that number is not that big, but we need to see that the compound annual growth rate of this market is very high. So actually from 2010 to 2020, the 10-year CAGR is about 25.4%. So this number is big. So based on this CAGR number, so we can calculate the expected market size in 2030. So that market size will be about 123 billion US dollars. That market is very huge. So that means additive manufacturing's expansion to all manufacturing industries is the coming future. As you know, lots of innovation through a 3D printing technology in various industries happens a lot recently. The first example, so this picture shows the metal 3D printed aviation engine fuel nozzle. So originally it consisted of 20 separated parts, but they designed one integrated part instead. The result was 25% reduction in weight and 5 times the strength. And the second example, it shows indirect 3D printing application. So it is a sand 3D printed optimized mold for hydraulic parts. So they could do size down and reduction in weight significantly. And there are lots of other applications of 3D printing. So these pictures show the applications of weight reduction using structural optimization and 3D printing technology. And the next is pain points and solutions in the foundry industry. So the reality of the foundry industry is tough. So there are lots of difficulties in the current foundry industry. And so these are the 4 major the challenges. The first one is about manpower, and the second one is about production efficiency, and third one is about the regulations, and the last one is about R&D. So this picture shows pain points, solutions, and core technologies. So the first column includes the major pain points: manpower shortage and demand for small quantity production for various kinds, and energy and environmental regulations, and insufficient R&D investment. And the second column is about solutions for the pain points. And the third column is about core technologies to address the solutions in the second column. And I can say that the 3D printing is a key technology to overcome the difficulties of the foundry industry. The next is introduction of SEM 3D printing technology. SEM 3D printing is a manufacturing technology to create three-dimensional objects by repeating the process of laminating sand layer by layer and selectively jetting binders on shape areas. The picture shows the first process of laminating sand. The thickness of the laminated sand is about 100 to 200 micrometer. The second step of the process is jetting binder selectively. The binder drops into the sand and then it is hardened in a short period of time. The third step is that the build plate is getting lower one layer, and then it goes back to the first step, and repeating the 3 steps until reaching to the height of the object. This is the short movie clip showing the whole process of SEM 3D printing and casting. These pictures show SEM 3D printed cores and molds for metal casting. As you can see, this MCV core needs to assemble several pieces of cores manually. But it can be 3D printed as a one integrated core and doesn't need to be assembled manually. And this hydraulic part mold is inseparable, so you cannot make it by using conventional pattern method. That means SEM 3D printing gives a huge flexibility of product design. So I summarized the effectiveness of SEM 3D printing technology into 6 directions: short development period, low investment cost, ability to produce a variety of small volume products, innovation of design flexibility, use of various materials, and quality improvement. So I explained the effectiveness of SEM 3D printing already, but many people assume that the mechanical properties of SEM 3D printed cores and molds are not enough to support metal casting. But that's not correct. I will show you the results of our experiments for that. The first test is about bending breaking strengths. We tested 3-point bending breaking strengths for Foundry printed specimen. It shows the Foundry printed specimen, and it shows the test equipment. And this table shows the test results for 8 different specimens, and the average bending breaking strength was 3.59 megapascal. Actually, the recommended minimum the strength is about 1.8 megapascal. So the result was much higher than that. The second test is about compressive strength. We tested compressive strength for the 3D printed specimen according to the standard. This picture shows the actual 3D printed specimen, and also it shows the test equipment. And this table shows the test results for 8 different specimens, and the average compressive strength is 6.09 megapascal. And actually recommended minimum strength for cores and moles is 3.9 to 5.8 megapascal for various applications. So the result was much higher than that. And the third test is about tensile strength. We tested tensile strength for the 3D printed specimen according to the standard. This picture shows the actual 3D printed dog bone specimen for tensile strength test. And this is the test equipment. And the table shows the test results for 7 different specimens, and the average tensile strength is 1.38 megapascal, and the recommended minimum value is about 0.5 megapascal. So the result was much higher than that. Also, we did additional experiments to compare to the conventional pattern-based method. When we made specimens for the conventional method, we used the same sand used for sand 3D printing. And this graph shows the sand particle size distribution. And this is the comparison results. It shows that the sand 3D printed specimens have much higher strength than the conventional pattern-based specimens in terms of all the 3 aspects: bending strength, compressive strength, and tensile strength. And the next is the air permeability of the sand 3D printing cores and molds. This is a topic that many people are most concerned about because the sand 3D printing is using very fine sand. Many people think that the air permeability of sand 3D printed cores and molds is very bad, but that's not true. So let's see how. We tested air permeability for the sand 3D printed specimen according to the standard. And this picture shows the actual sand 3D printed specimen for air permeability test. And this is the test equipment. And this table shows the test results for 10 different specimens of 2 different methods. The results show that the air permeability of the sand-3D printed specimens is more than 1.8 times higher than that of the conventional method. So the left-hand side is sand-3D printing result, and the right-hand side is conventional method result. In addition to that, we did additional air permeability test using 3 different kinds of sand. So this is the particle size distribution differences for 3 kinds of sand. So this color is the particle size distribution for silica sand 140, and this is for the artificial sand 145, and this color is for the silica sand 90. So the number means the diameter of sand. And these are the pictures of the microstructure for the 3 different kinds of sand. As you can see, the sphericity of the natural sand, these 2 are natural sand, looks not that good, but that of the artificial sand looks good. And this is the test results. So this is the result of the silica sand 140, and this is for silica sand 90, and this is the result for the artificial sand 145. It shows that the larger the size, the higher the sphericity, the better the air permeability. Conclusions. So additive manufacturing is rapidly expanding into all manufacturing industries. And sand 3D printing is positioned as a key technology to overcome the challenges of the foundry industry. The core or mold made by 3D printing satisfies all the conditions sufficient to produce products through metal casting. And the mechanical properties of the core or mold fabricated by sand 3D printing are much superior to those of the conventional pattern method. And the air permeability of the core or mold fabricated by sand 3D printing is much higher than that of the conventional method. And the last thing is about materials. So we did lots of projects using sand 3D printing for various kinds of metals. These pictures are to show our successful outcomes, such as gearbox part, pump box part, pump impeller, military car parts, power plant impeller, and agricultural machine part. These prove that cores and molds made by sand 3D printing are suitable for casting all metals, including aluminum, cast iron, cast steel, copper alloy, and so forth. So I can say that the sand 3D printing is becoming the next generation technology for innovating foundry industry. And as you know, the 74th World Foundry Congress will be held in Korea during October 16th to 20. Please join the Congress and let's meet there. Okay, this is all of my presentation. Thank you very much.
This brings us to the end of the session
Hello,
one, and we'll reconvene at 12:15 for the remaining two videos at the same hall. Thank you everyone for being here over this session. Thank you.